Alright, hello guys, and welcome back to our next lesson. We are now in section 6 of chapter 1, which is titled Inverse Functions. So let's go ahead and get started. First of all, let's start out with the definition. So an inverse function is a function that undoes the action of another function. So in other words, let me give you an example of what that means. So let's go back to a couple lessons ago. You learned the parent functions. So we have the parent function of x squared and the parent function of the square root of x. Well, these two functions are known to be inverses of each other because algebraically they cancel each other out. So think about when you are doing operations and you are solving equations. If you ever want to get rid of a square, you square root it, and if you ever want to get rid of the square root, you square it. So in other words, those functions itself, they undo each other, and that's why they are called inverses of each other. So that's what an inverse function does. Okay? Now, how do you express or how do you communicate that a function is an inverse of another function? So there's some notation you're going to have to get familiar with. So we already proved that these two are inverses of each other. So if you want to communicate it through writing, you could say that f of x is equal to x squared, and then you can use this. It looks like a power, but it's not a power, so it's a little -1. This right here says inverse function of f. So this is f of x, and this is inverse function of f of x is equal to the square root of x. So that's just some notation that you can get used to. Okay? All right. Now that you know what an inverse function is, we got to figure out how is it that we find it. Do all functions have an inverse function? Or how do we figure all that out? Okay? So let's start out with one topic or one idea, which is known as the one-to-one function. Okay? So let's go ahead and start out with that. So a function f has an inverse if and only if for every y in the range there is only one x value in its domain for which f of x is equal to y. Okay, that is just a fancy way of saying, hey guys, every single point on that graph has to be unique. For every x value, there has to be a unique y value. Okay, so if you plug in 1 and then you get 3 out of it, there is no other x value that would give you a 3. Okay, that's what it means to be a one-to-one function. So now if you read that definition, that is a requirement to be an inverse. So as we're studying this idea of having an inverse, the very first thing you should really consider is the function one-to-one? Because if it's not, then you can automatically say that that function will not have an inverse. Okay, so let's do a graphical example and see what we're talking about. Okay, so here we have a function. This is actually the parent function y equals x squared, since I've been using it for the previous two examples. And we know that the parent function of a quadratic has the point 1, 1, right? If you plug in 1, you get 1. But also if you plug in -1, you get 1. So based on what I just previously said about this definition, for every x value, there has to be a unique y value. Well, notice that for this, if I plug in -1, I get 1. If I plug in 1, I get 1. So this y value is not unique to this x values. Like, there's not a point, like it's a repeated y value, therefore it's not unique. So we can then say that because there's not, for every x value, there's not a unique y value, it's enough for us to say that this function is not one-to-one. And if that function is not one-to-one, then it's enough for us to say that it doesn't have an inverse. Now, that contradicts a little bit of what I just said here. I mean, I literally just said that these two are inverses of each other, and now this is saying that they don't. So how is it possible that this is proving to us that this is not that it does not have an inverse? And we'll get to that here in just a minute. Okay? Now, for you, I mean, it could be very difficult. I mean, I chose this example because it's very easy enough for you to recognize these values and come up with this table real quick and know that it's not a one-to-one function. But there are more complicated functions, and if you want to figure out whether or not they're one-to-one graphically, it would be helpful to use something known as the horizontal line test. As you can see here in green, I drew a horizontal line through the graph. If that horizontal line touches the graph at more than one point, then it is said to have failed the horizontal line test, which means that it is not a one-to-one function. And if it's not a one-to-one function, then it doesn't have an inverse. Now think about why is it that the horizontal line test works. Okay, a horizontal line test, go back to, like, for example, your parent functions. If I tell you y equals 2, that's a horizontal line, right? At 2, so you're always at 2. Well, what that means is that if you draw, for example, a horizontal line here at 1, that's the y value of 1. Notice that if I'm touching at multiple spots, that means that there has to be a corresponding x value for me to be there, and that's the reason why the horizontal line test works. Okay? So that example is not 1-to-1, so it doesn't have an inverse. Another example would be this one right here, and notice I drew several horizontal lines to make sure that you understand this. It doesn't matter where I draw the horizontal line, I will only be touching at one point. Therefore, you would pass the horizontal line test, and that function must be 1-to-1 and should have an inverse. Okay? So, now that you know how to determine how to find whether a function is 1-to-1 by looking at it, let's discuss the idea of how do we figure out if a function is 1-to-1 algebraically. Okay, so algebraically we're going to have to take this into consideration. So let's go ahead and read the definition, okay? So once again, is to prove that this is 1-to-1 function, which is a requirement in order to have an inverse. That's the reason why we're discussing this, okay? So a function is said to be 1-to-1 when for an a value and a b value that is part of the domain of that function, okay, the outputs are equal to each other. So remember, if you have an x value and you plug it into a function, then you get an output, so you get a y value. So it basically says that if you have a and b and you plug it into the function, if the y value is equal to each other, then that implies that a would have to be b. That's the only way that this could be 1-to-1. So think this through, because I just said this earlier. For every x value, there has to be a unique y value. So if these two were different, but they're yielding out the same y value, then it wouldn't be a 1-to-1 function. But if these two are the same, they should yield out the same y value, because it's the same, right? It's a unique value. So let's go ahead and give an example and try it out. Okay? So let's say, is the function below function 1-to-1? So we've got a function, let's say that we have f of x is equal to 5 minus 3x over 2. Okay? So if this is going to be true, then that means that this statement has to be true. So in order for us to do that, we have to figure out what f of a is and what f of b is. So what we're going to do is we're going to find out what is f of a, and we're going to set that equal to f of b. So that's what we're going to do. We're going to plug in a first. So we're going to have 5 minus 3a over 2. Is that equal to, so I'm going to question it, 5 minus 3b over 2. Okay, so now we're going to solve this. Okay, so notice that on both sides of the equation I have a 2. So I'm going to be able to multiply both sides by 2. So that 2 should cancel that 2 out, which would leave us with 5 minus 3a. And we're still questioning this. Is it equal to 5 minus 3b? Okay. So now we're going to keep, I can subtract 5 from both sides. So if I subtract 5 from that side and 5 from that side, I am left with negative 3a. Is that equal to negative 3b? So now I can divide both by negative 3, and now we can see that a is equal to b. And that was a requirement. Think this through. If you're able to do the algebra and go all the way down and prove that a is equal to b, then at that point we can say, then therefore f of x is 1-to-1 and must have an inverse function. Okay? So that's how you determine algebraically whether a function is 1-to-1. And the reason why I'm being so persistent with this idea of the 1-to-1 should be obvious, and that's because one of the requirements for a function to have an inverse is that it must be 1-to-1. So you have to first figure out whether a function is 1-to-1 if you are going to pursue the idea of an inverse function. Okay, so now you're like, okay, cool. Now we know whether a function is 1-to-1, but how do I find that inverse? Okay, so yes, I found out that it does have an inverse. So how do I go ahead and find the actual inverse? So let's go back to that example that I gave you. So that example was, let me look back at this page. It was f of x is equal to 5 minus 3x over 2. So 5 minus 3x over 2. Okay? So yes, it is 1 to 1, which means it does have an inverse. So let's go ahead and find it. Okay, so the procedures for finding an inverse. Step number 1, you are going to switch x and y variables. So what that means is, technically, you remember that f of x is the same thing as y. So we're going to switch them, which means that this says x is equal to 5 minus 3y over 2. Step 2 is going to be to solve for y. So we're going to solve for y. So in order for me to do that, I'm going to multiply both sides by 2. So that's going to give me a 2x is equal to 5 minus 3y. I'm going to subtract 5. So that's going to give me 2x minus 5 is equal to negative 3y. And then I'm going to divide by negative 3, which is going to give me to y equals 2x minus 5 divided by negative 3. Okay? So then our step 3 would be to replace y with proper inverse notation. Okay, so in that case, because we started with f of x, that means that the proper notation is going to be the notation that we spoke out a few minutes ago. So now it's inverse of f of x is equal to. Now I'm just going to use a little bit of algebra to clean this up. I don't like that negative there. So if I bring the negative to the top, and I distribute, that's going to give me 5 minus 2x over 3. And then that would be the inverse of f of x. Okay? So very simple 3 steps. You're going to switch x and y, you're going to solve for y, and when you're done, you're going to replace y with the proper inverse notation. Okay? Now, remember, I like to keep this video short and not do a whole lot of examples because I want to make sure that you can actually practice this on your own on the homework, and I think one example should be enough. So practice your homework. The algebra will definitely get heavier. When I say the algebra, I mean the arithmetic, okay? So you make sure that if you have any questions, you come ready and ask those during class, okay? Okay, it is now in the video that I want to go back to that idea of the graph of x squared. So earlier, right at the beginning of the video, I said that x squared and the square root of x were inverses of each other, right? And then we discussed the idea of being 1 to 1, and we found out that in order to be 1 to 1, it must pass the horizontal line test. But once we graph x squared, we realized that it didn't pass the horizontal line test. So how is it possible that something that does not pass the horizontal line test can be claimed to have an inverse? Well, let's discuss that idea. Okay, first of all, let's talk about the function y equals root of x. So if you remember, the square root of x is a function that looks something along these lines here. So it's just a sketch, not the exact graph there. So it looks something like that. And x squared, once again, is a function that looks something like this. It would go up in that direction, and then it would go up in that direction. Cool? So let's talk about this. So, okay, so let's just analyze square root of x. So, by the way, this is y equals x squared. If we look at square root of x, if we were to perform the horizontal line test, you should see that it definitely passes. So it should have an inverse, right? But if we perform the horizontal line test on y equals x squared, it doesn't pass the horizontal line test. So that means that it cannot possibly have an inverse function. However, it can. And the way that we can do that is by, hey, you know what? Asking yourself, what is making me fail? Why am I not being able to pass the horizontal line test? So when we analyze this graph, you should realize that it's because this graph happens to be kind of symmetric, right? You got the left and the right side being the same. So what if I got rid of this part? What if this part didn't exist and only the right hand side existed? Then that would totally pass the horizontal line test. And if it passed the horizontal line test, then it would have an inverse. And now we're like, okay, awesome. It passed the horizontal line test, it has an inverse, and we know that they're inverses of each other. So in order for, just because something fails the horizontal line test from the beginning doesn't mean that you cannot have an inverse. Maybe you just need to get rid of part of it. And in mathematical terms, what you're really doing is restricting the domain. What that means is that in order for x squared to actually have an inverse, you have to restrict its domain to 0 to infinity. And then you're going to be able to have an inverse. Okay, so you're going to have to keep that in mind. Sometimes you are capable of restricting the domain in order to have an inverse. Okay, now that we're here, let's talk about something that I find very interesting myself about inverses and their graphs. Okay, again, I did not draw this to scale, but as you can see here, it's very interesting. Okay, there is symmetry going on here. Okay, and I'm going to go ahead and add a little extra here so you maybe can see it. Okay, if I were to draw a line here, so I'm going to use a dotted line instead. And again, keep in mind, I did not draw this to scale. But if I did, do you notice how both sides of this line, if you were to fold along that line, this part of the graph would match with this one, and this would match with that one. Again, if I had drawn it perfectly, then they would. So inverse functions, have symmetry with respect to a very important parent function. And that function would be, think this through, what parent function looks like this? And that would be the linear function. If two functions are inverses of each other, when you graph them, if you were to put y equals x into that window and you were to pretend to be able to fold along that line, you would have symmetry along that line, and that would prove to you that they're inverses of each other. So notice once again, if I were to draw back this part here, well, for one, it fails the one-to-one test, the horizontal line test, so it doesn't have an inverse. But if I erase it, then the symmetry would definitely be there, and that would confirm that they are inverses of each other. All right. And the last thing we're going to do here is, what if instead you are being asked to verify? So to verify that the following functions are inverses of each other. So in other words, I mean, you're going to be given two functions, and it's going to be your turn to prove that they are inverses of each other. Okay. So let's say that you're given the following functions. So f of x is equal to, let's do something simple. Let's do 4x. And let's say that g of x is equal to x over 4. Okay. So you've got a bunch of tools under your belt right now to do this. Okay, first of all, is like, okay, you could switch x and y on this one. So you could say this is x is equal to 4y. You divide by 4, which means that y is equal to x over 4, which means that f inverse of x is equal to x over 4. And as you can see, then yes, this function and this function would be inverses of each other. Fantastic. Okay, we could also graph this, right? So we could have this. Here's my x, here's my y-axis. Now, this is a rough sketch one more time. So 4x would be, let me use different colors. So for 4x, I'm going to use this purple. I don't know if you can actually kind of tell that on the video. So let me use the black, okay? So 4x, I'm going to use the black here. So at 0, I'm at 0. At 1, I'm at 4. So let's say that this right here is 4. And this is 1. So at 1, I'm at 4. At negative 1, I'm at negative 4. So 1, 2, 3, negative 4. So I'm down here. And this graph would look something like that. Cool, so this would be y equals 4x. Let's say I'm going to use green for y equals x over 4. So if I plug in 0, that would be 0. If I plug in 1, that would be 1/4. So 1/4 would be very little here. Let's say that I plug in, let's go to 2, let's go to 3, let's go to 4. If I plug in 4, 4 over 4 is 1. So 4 over 4, that would be 1 right there. So that's -1, -2, -3, -4. If I plug in -4, I'm going to get -1, so that would be about right there. So then notice that if I draw that line, that would look something like that. Cool. So I would have those two graphs there, and then I could remember if I do y equals x, so y equals x would look something like this, where it goes through 0, 0, 1, 1, 2, 2, etc., etc. And then you should then notice that there is a symmetry between the y equals x, so therefore there must be inverses, and you can also prove it. Remember this point right here, if I actually write down the points, this point right here is 4, 1, and notice how this point right here is 4, 1. If you switch the x and the y, then you get the points on the other graph, and that is a property of inverse functions. So that's another way to verify that the functions are inverses of each other. So one is to actually find it, two is to graph it. But there is a third method, and that third method is called composition, which is what you learned last time. So let's go ahead and talk about that. Okay? If f and g are two functions such that f of g of x is equal to x and g of f of x is equal to x, then f and g are inverses of each other. Isn't that pretty cool? Think this through. It basically says, if you were to do a combination of the two functions, f of g of x, and notice how it says and, so you have to do both. You have to prove. And if both f of g of x and g of f of x gives you x, then that means that they're inverses of each other. And I find this very interesting. Why x? Well, think this through. Go back to the example that I just gave you graphically. What is the line in which they're symmetric? X. And that is the reason why composition has to be equal to x, because of the symmetry that exists between them. Okay? So to me, that, I mean, I don't know about you, but to me, that is just so cool. And I mean, obviously, there's so much more, right, to it, you know, as to y is equal to x. There's a beautiful proof out there that you can actually look at. Go to Google or YouTube, and you can find a proof of this. But to me, you know, we're not in that class in which we're learning the theory behind of why it works. I'm just teaching you that it works. But to me, it's so amazing. But anyways, let's go ahead and do an example of that to make sure that it does work. So let's go back to these functions. You still have f equal to 4x and g equals to x over 4. So let me rewrite that. Okay. So we're going to do f of x equal to 4x, and then g of x equals to x over 4. And now we're going to use this third method. So first, we're going to say, what is f of g of x? Well, remember, I'm going to do 4 because that's the outer function, parentheses, and I'm going to input the other one, so x over 4. The 4's cancel out, and it gives you x. Now I'm going to do g of f of x. So the g function, instead of x, I'm going to use parentheses. I'm going to put a 4 here. Inside the parentheses, I'm going to put the other function, which in this case is 4x. The forces cancel out, and it gives you x. So the fact that they're both giving you x means that f and g are inverses of each other. So there you go. 3 ways for you to verify that two functions are inverses of each other. Now, keep this in mind, and please pay attention to this last statement I'm going to say. For my class, when I ask you on the test to verify whether a function is whether the functions are inverses of each other, I will specify what I want you to do. So I could say verify through the use of composition. Then you must use composition to prove it. Okay? Or I could say verify graphically. Then that means you're going to have to graph it and then show me graphically. Okay? Or I could just say verify algebraic. Okay? If I don't tell you what method to use, then you are more than welcome to use any method to use to prove that two functions are inverses of each other. Okay, so to recap, hopefully this video, I know it was a longer video than usual, And even as long as that video is, it almost seems like I didn't give you enough examples. But at least you have an example for each type of topic that you're going to run into for this homework. You should be able to, number one, now you know what an inverse function is. Okay. Number two is you know how to determine whether a function is one-to-one. And if a function is one-to-one, then it means it has an inverse. Cool. Number three is you know how to find an inverse by simply switching x and y, solving for y, and replacing the notation with inverse. And last but not least, you should now be able to verify whether two functions are inverses of each other through 3 techniques. Okay? That is all for me today. Hopefully this video helped you out, and I will see you next time.